I'm very excited to be speaking here as the first invited speaker. So I really hope that this series of lectures brings a lot of fruitful discussion for everybody. And yeah, I'm as Barbara already told, I work at the University of Leiden. I also want to say that this is joint work with my colleague Lauren Fontaine. And in the project, we're basically working with bird models, applying them to historical languages. So today I'm going to be talking about that project, and in particular, let's see, yeah. I'm going to be also talking about the application of these models to the task of word sense disambiguation. First, I'll give a little bit of background on this project, and then I'll introduce this idea of non-parametric classification for word sense disambiguation. And if there is time, we'll also go a bit beyond word sense disambiguation to other applications of the same method that we've been experimenting with. Okay, so let's start with this. What is the background to this project? So we've been already about 2 years working on developing BERT models for historical languages. There is already a version of something called MacBERT, which is a language model that is pre-trained for the period of 1450 to 1950. So it's 500 years of English that we collected from different sources. There is also an ongoing model that's being trained and tested right now that is basically the same model, but with a case version for named entity recognition, because we figured that many people are interested in that. So that's also part of it. And then for that, we worked out HiSBERT, which is a similar model, covers a little bit smaller range, going from 1600 to 1940. And we are currently working on an improved version of it that will have more data and cleaner data, which is very important as we've found out. And yeah, so the idea behind the project is ultimately to basically provide some kind of research infrastructure to people interested in working with historical text, doing things like part of speech tagging, morphological annotation, word sense disambiguation, something I would call ad hoc classification, which is basically any given manually annotated data set that a researcher may be interested in automating. So that can be really a very large number of things. I have some examples at the end of this presentation, so I won't go into detail now. There are also tasks from information extraction, like named entity recognition, relation extraction, etc. And then perhaps more theoretical questions like lexical change and semantic evolution. And so I'm not going to go too much into the details of what BERT is and how it works. I will just say that typically once you have this big model that has been pre-trained on a lot of training data, the next step is to gather some manually annotated data that you're interested in having a model to classify. And then you'll have something like this. So you'll have your model run over sentences. Here I'm showing 2 sentences, but for the sake of the argument, we can forget about the second one. Imagine that there's only 1 sentence. We're processing all the inputs. And then at the end, we have a sentence that we want a class label for it to be predicted. Imagine that this is word sense disambiguation. So we'll have a sentence exemplifying a particular word, and we want to know what of the word senses of that word is actually being represented in the sentence. And this is how it's usually done. I'm going to highlight a number of issues with this approach, which is that basically every time you have a new task that you want to do, you have to train a new classification layer. So once you're running this the model over your sentences, what you're doing during fine-tuning, so you have your pre-trained model and you do fine-tuning on the task that you're interested in doing. What you're usually doing with this approach is fine-tuning the weight of a linear classification layer that is put on top of the BERT model. And as we know, these models are very appealing because they have something that is called high sample efficiency, which means that we don't need a lot of manually annotated data for the model to be able to generalize. So we can fine tune these models on not too many data points, and we'll still get very strong performance, and we won't have to deal with any of the manual feature engineering that is very time consuming. This is one of the reasons why we're interested in developing these models in the first place, because we believe that this is a nice effort to get people in the digital humanities community to actually do the classification tasks that they want without too much work. Yeah, I'm basically repeating a lot of the stuff that I just said. Right. So what is the problem with this standard approach that is, I don't have a name for it, but it's basically the normal fine-tuning with a linear classifier, is that in many cases we want to do classification for new tasks for which we don't necessarily want to fine-tune another linear classification layer. And instead of doing that, what I'm proposing to do is something called non-parametric classification. And the idea behind non-parametric classification is that we are not gonna be using any extra parameters to learn to do the task. This is there is another motivation for doing this, which is that these methods that do not rely on fine-tuning external parameters, they're actually very efficient for future learning scenarios. So given a very short number of instances, we can still learn to do the classification in a very efficient way. Right. There are multiple instantiations of this idea. You might have heard of metric learning, of prototypical networks, matching networks, or even meta learning. These are all related ideas. They are not exactly the same idea, but they belong to the same family of approaches. I'm gonna illustrate this because I understand that this is hard to grasp in the way I'm describing it very generally. So I'm gonna show an example following the word sense disambiguation experiments that I'm also gonna illustrate later on. So we all know what word sense disambiguation is as a task. Imagine these two sentences. We have the sentence, I can hear bass sounds. And in this case, we know that the word bass means a low frequency tone. And there is this other sentences that is, they like real bass. And if we don't have access to the phonetics of these words, we don't really know which word is being represented in each sentence unless we actually understand language. So the idea is that given that BERT models produce word embeddings that are contextualized, so basically we have a word embedding that represents the meaning of each word in the sentential context in which it appears. It seems that BERT-based word sense disambiguation is like something that we get pretty much for free. We just have to compute the embeddings for all the words that we want to disambiguate, and then we can do some kind of clustering or identify clusters in the embeddings in the embedding space that we get, and we should be good with that. And the reality is that we are not really that good. I mean, this is an ideal scenario that I am showing here. This is not real data. I'm just showing, imagine that we have three word senses, 0, 1, and 2, and I'm representing the embeddings for the words in my sample. And if everything goes well, I should expect something like this to show up. In reality, if you use BERT and do it like this, and you evaluate on traditional word sense disambiguation benchmark tasks, you will see that it's not that nice. That's what I'm seeing here. I'm gonna show an example of what you actually get. Here I'm showing two examples. Let's focus on the one on the left. It's kind of the same visualization as before, but this is now real data from my experiments. And what we get, if we don't do anything to BERT, we just take the frozen embeddings, as they're usually called, we get a a cloud like this, where you can kind of imagine some clusters, but if you evaluate this clustering, you won't have very high performance. And the idea is that we apply this non-parametric fine-tuning, and you end up having something like that. In some cases, of course, this is not like a silver bullet that works for everything. So, but in many cases, what you get is a pretty much a pretty clustering of your word senses. Yeah, this is one of the problems that we're trying to tackle also with this approach, is that once we do this fine tuning, because we are not using any extra parameters for disambiguation of the different lemmas in our data set, that means that we can also apply it to lemmas that we haven't seen during training and still get some decent performance. And this is what I'm going to show now. But for the rest of the presentation, what I want to do is to actually give the intuition behind this approach. All right. So the way this works is doing something called episodic training. Each episode, I'm sampling lemmas from my dataset. So here I'm selecting the lemma base and the lemma spicy. And here I see that each of the lemmas has two word senses, which is A and B. So first I sampled these two lemmas from the entire dataset, and then I'm sampling one at a time. What I'm going to do is I'm going to start projecting the embeddings for so each of these instances here, each of these A's are examples in my training set. And the next thing I'll do is I'll select something that is called a support example. So these support examples are going to be used in order to compute some kind of word sense embedding. And so I'll start sampling support examples. I'll put them on my 2D space. I'm representing this with 2 dimensions, but you have to remember that these embeddings are something like 728 dimensional. Right. Then I take another support example. Then I go to the other word sense and I do the same thing. I embed my support examples, and I'm selecting 3 in this case. And the next thing I do is I compute a center rate for each of the word senses. So as you see, I take the middle point between the 2 support examples, and that's going to be the representation of my word sense. I go to the other word sense, I do the same thing. So now I have these 2 center rates. And the next thing I do is I go and take my query examples, and these are going to be the examples that I want to classify. I put them on my 2D plane, and then I measure the distance to the center rates. And sorry, going back, I measure this distance, and I use this distance to produce a classification. So here I'm doing the same thing for the other word sense. And this one is also being classified to the closest center rate. All right, so once I've done that, this is now a real example with all the points, all the support examples, all the query examples, and my center rates. You can see the different center rates are being represented by squares. Here there is one, here there is another one. Then I have query examples, which are represented by crosses, and then I have support examples, which are the dots. So this is how training proceeds. So but basically what I'm doing is I'm fine-tuning BERT to produce embeddings that are that will end up closer to their centroid, to the same word sense as the examples belong. And I'm not using any extra parameters to do this. I'm just fine-tuning the parameters that come from BERT. While I do this, I need to make a number of choices. For instance, I need to pick a distance metric. I could use Euclidean or cosine. I also need to find a way to generate centroids, which in these examples I was showing is just taking a simple average function. And then there are a number of training hyperparameters. For each episode during training, I need to select how many support examples I'm going to use, what is going to be the proportion of query examples in each batch, etc. And all these parameters actually matter. So you need to make smart choices there. And then this is all good and nice, but why is this supposed to work? And basically, the idea is that while we do this, what we are actually doing is kind of matching the training and test conditions. So the same way I'm gonna apply this model once it's fine-tuned is the same as when I'm fine-tuning it. That's something that is usually found in future learning approaches. And then what is more important even is that what I'm actually doing when I'm telling BERT to do this task is that it tries to remove any information from the embeddings that is not relevant for disambiguating words. Basically, any dimensions in my embeddings that are not correlated with lexical semantics, I'm going to ask BERT to remove. And that way, I get these nicer clusterings when I'm done fine-tuning. So let's move on to the experiments. I'm going to show examples. I think I also have data for Dutch, but I'm not sure if I have them on these slides right now. But for English, what we do is we went to the Oxford English Dictionary, which is a very large dictionary featuring something like 600,000 lemmas and documenting a lot of a very long range of English. And there, what we have is very nice classifications or classification of word senses that is documenting the use of particular word senses over time. I'm showing here an example for the word wife. You can see the classification is a bit lower down. It's you see we have word sense number 1, and then 1.1, 1.2, 1.3, 2. Etc. And it goes all the way down. So we went to the website and started scraping a number of lemmas, something like 3,000 lemmas, and collected all the quotations with their years of appearance. And yeah, as I was mentioning, for Dutch, we also have something called the Woordenboek der Nederlandse taal that works very similarly, although I found that there is a very large skew in this dictionary with respect to the Oxford English Dictionary, which I think affects the results as well. All right, so for these experiments, we didn't really use all the data. So we restricted ourselves to something like 800 lemmas per language, which gave us something like 22,000 senses and about 120,000 quotations. We reserved 10% of the lemmas for future evaluation. So that means that 10% of these lemmas aren't used at all during training. So we only use them for evaluation, few shot or zero shot evaluation. And we also have an in-domain evaluation, which means that we evaluate on lemmas that we do see during training. So something like 50% of the sentences of each word sense are used for evaluation as queries. And yeah, we're gonna report results on this method for both modern day BERT and historically pre-trained BERT, which is MacBERT. And we're gonna show well, we're quantifying this metric in terms of macro and micro F1. This is because we have skews, so the word senses are usually very skewed. All right, let's see some results. So first, I'm showing the in-domain results. So this is, again, lemmas that were seen during training. So if we start on the left side, we have BERT and MacBERT, distinguished by the color. And we're also seeing 4 lines. So 2 lines are dashed and the others are straight. And the difference is between applying the fine-tuning method and not applying a fine-tuning method at all. So the ones that are below the dashed lines are basically just taking the word embeddings from BERT. And the dashed line here in the middle is the most frequent word sense baseline. And so the first thing that we can see if we focus on micro F1 is that our word embeddings, the contextualized embeddings with any further fine-tuning are actually underperforming the most frequent baseline, most frequent word sense baseline. So that's actually a bit worrying because our hypothesis was that these embeddings should be already pretty good at this task. Turns out that they are not that good. If we go to macro F1, then we get a different picture. So we are overperforming the baseline, but still what is interesting to see in these graphs is that we are pretty much below the fine-tuning approach, the non-parametric fine-tuning approach. And again, if we focus on difference between the historically pre-trained model and the modern model, we see that the historically pre-training is actually quite useful. So it gives us something like, I don't know, 0.1, a bit less maybe, extra points. So which is, it's a nice result. And for Dutch, we actually see quite a similar picture. The main difference though is that the micro F1 baseline here is very, very high. And this is because of what I was hinting at before, that the word senses are very, very skewed. In this case, if we look at macro F1, we see that the baselines are actually not overperforming the baseline either. And by the way, I realized that there's something here that I did not explain, which is the x-axis. And this is also interesting because what we're doing here is the x-axis is basically telling us how many support examples we have during inference. And we go from 1 to 5, 10 to 20. And we see that already by just showing one support example, so basically computing the sense rate on the basis of a single example, is giving us a performance that is not too far below what we get if we get 20 support examples. So this is also nice because the idea of this method is that you would basically gather sentences for the lemma that you want to disambiguate, and you'll have to kind of manually annotate the different word senses in your lemma, and you'll have to annotate a number of examples for it. What we're showing here is that you might not need too many examples for getting the performance to which this model converges, which is something about 0.7 micro F1. Of course, this is not perfect. We're still very far away from something like that, but it's a nice result considering that the method doesn't really require much. And so this is for in-domain data. Now let's move on to what is more interesting, which is what happens when we look at lemmas that were not seen during training. So these are lemmas the model has not been exposed to at all during training, and we have the same thing now. The x-axis is how many support examples per word sense we're using. And what we observe in general is a pretty similar picture to before. Of course, results are a bit lower than before, so we're not really reaching 0.7 at any point. And we see that we need a bit more support examples here than we did with the in-domain evaluation. Again, our baseline and the embeddings straight out of the model without any further fine-tuning are showing. For Dutch, we have again similar picture where the most frequent baseline is actually quite high for micro F1 and quite low for macro F1. And again, the historically pre-trained models are outperforming the other models. Okay, so this is all I had to say about word sense disambiguation, but there are some applications that go beyond that and basically apply the same kind of method, the same kind of fine-tuning to other tasks. So here we are not so much interested in this out-of-domain or held-out evaluation, where we look at what happens when we have lemmas, or basically when we try to apply the model to a different task, a different path-related task. So here we're just using this method to fine-tune our model to perform some kind of classification. And we've done 3 experiments that I'm going to summarize very, very quickly. The first one relates to fire metaphors. The idea that we were after is that we are basically looking into whether particular events in history that cause an increase in the usage frequency of fire words in the literal sense may also trigger a change in the frequency of the figurative uses. And the idea is to investigate whether the Great Fire of London, which occurred in 1666, did trigger a frequency-driven change in the semantic structure of fire words. So what we did is we took examples of these 5 lemmas: fire, flame, ardent, blaze, and burn. And we did a two-way classification here. So we're classifying the sentences according to whether they're used in a literal or a metaphorical sense. We randomly sampled 300 instances per lemma from the lemma corpus, and we applied this method along another 3 different methods that I'm showing here. So the other method is sentence classification fine-tuning. This is basically doing this linear classification layer on top of BERT. And then we also did KNN using frozen embeddings, and SVC also using frozen embeddings. We applied tenfold cross-validation to get some idea of the variance in the evaluation. And what we see is that we're showing here precision, recall, and F1. This is a lot of numbers, I know. So let's focus on the most important one, which is when we combine all the data sets, so all the lemmas taken together, and we look at the mean F1, and we can see that this method, without using any extra parameters, is actually giving us something like 4 points above the next competitor, which is the sentence classification fine-tuning. There's another experiment we did, which involves the concepts of mass and weight. The idea here is that following Isaac Newton publication in 1687, there is now in the scientific community a differentiation between the concepts of weight and mass, following the introduction of gravitational theory. And here we were interested in seeing, for instance, how the adoption of the innovative concept of weight spread. So we're interested in the diffusion of this concept. Is it more based on other networks or disciplines, and also the effect of this new concept on other uses of mass and weight? And before you can do something like this, you have to go through a very large data set of instances of mass and weight and manually annotate them. So what we figured is maybe there is a way we can automate this work, and the idea is the same as before. So we went to the Royal Society corpus, took something like 1,500 samples. There are more than 50,000 instances, so manually annotating this would be a lot of work. So we were considering automating this, and what we are showing here is the results of these experiments, where we're trying to automate the classification. In this case, we have a 6-way classification. This is really word sense disambiguation. So we have 6 word senses with a considerable skew. And here I'm just showing 2 word senses because I didn't want to put too much information on this slide. But basically, there is the sense M, which is when whether mass or weight refer to the concept of mass, how much matter is with. Oh, I'm sorry. I think I'm talking too fast. All right. Yeah, so how much matter is within an object. And then we have another concept, which is the concept of weight, which is the one that refers to this force that was introduced by gravitational theory. So again, we look at the examples, at the results. We focus on the micro F1 of when we take into account all the lemmas, not just mass or weight. And we see that we are actually getting a much better result than any of the competitors. So the difference here is quite staggering indeed. There's the last experiment that I will show, which involves the role, something that we could call semantic roles of the semantic field of scent. The idea here is that generally cultural and ideological dimensions of discourse are often reflected in the semantic roles that we assign to particular individual or objects. A very good example is how the online press reports in the UK student fees protest in 2010 were more likely to assign agent roles to students and recipient roles to police agents. And we have a colleague who is interested in doing some similar research into the role of assent-related concepts over time. And the hypothesis, the working hypothesis, is that in earlier literature, these concepts were represented as more autonomous and agentive things that affected people. And over time, this has become more of a passive role. Again, the situation is that there is way too much data to manually annotate, so we want to somehow automate this. And we do this by doing a three-way classification. In this case, we have the agent role, the object role, and the patient role. And we focus on Dutch now. It's 17th century and 18th century Dutch. And the concepts are her and rug, which are kind of synonyms. And what we did is we sampled 500 instances per lemma and manually annotated them. And again, we did some tenfold cross-validation with our same competitors. And here we have a similar result, although for micro F1, we see that the concept of rug did not really, so the metric fine-tuning approach did not outperform the sentence classification fine-tuning. All right, so this is all I had to show. Now I'm gonna show you a little bit of how this is actually done. I have a notebook here. I'm gonna quickly go through this. And Barbara, since now we're not being recorded, I figured that maybe we can have some more interaction. So if there are any questions while I go through the cells, I'll be happy to take questions. I don't know